Welcome friends. In the previous classes, we discussed the predictor-corrector formulae, namely Euler's predictor-corrector formulae and Milne's predictor-corrector formulae to solve a linear differential equation of the form dy by dx is equal to f of xy such that y of x naught is equal to some y naught. In this session, I shall introduce another predictor-corrector formulae, namely Adam-Bashforth's predictor-corrector formulae. By Newton's backward interpolation formula, we have Z is equal to Zm plus u into del Zm, u into del Zm. Del means the backward difference operator, del Zm plus u into u plus 1 divided by 2 factorial into del square Zm plus u into u plus 1 into u plus 2 divided by 3 factorial into del cube Zm plus etc. Here Z is equal to dy divided by dx. Dy by dx is denoted by Z, that is this is equal to y dash. Zm is equal to ym dash. Del Zm is del ym dash, etc. These are the notations used in this formula, and u is defined as x minus xm divided by h, that is x is equal to xm plus u into h. H is the step size. Now, we integrating this expression both sides with respect to x between the limits xm and xm plus 1. We can write in the left hand side as ym plus 1 minus ym, which is equal to h into integral from 0 to 1 Zm plus u into del Zm plus u into u plus 1 divided by 2 factorial into del square Zm plus u into u plus 1 into u plus 2 divided by 3 factorial into del cube Zm plus etc. du. Here the integration is with respect to x. Therefore, we can write dx as here x is equal to xm plus uh, means if we differentiate we can write dx as xm is a constant, therefore derivative of xm is 0. H into h is again a constant, derivative of u is du. That is dx is equal to h into du. Therefore, we can write like this when we integrate both sides of this equation with respect to x. The limits for u are 0 and 1. The limits are 0 and 1 because for x is equal to xm, when x is equal to xm, we can write this implies u is equal to 0. When x is equal to xm plus 1, we will get xm plus 1 minus xm divided by h. Xm plus 1 minus xm means h divided by h, which is equal to 1. Therefore, the limits of integration will become 0 and 1. Now, we integrate each terms separately. First, integral from 0 to 1 Zm du. Zm is a constant. Integration with respect to u means integral du, which is equal to 1 u between the limits 0 and 1, that is 1. Integral 0 to 1 u du, which is equal to u square by 2 between the limits 0 and 1, that is 1 by 2. Now, integral from 0 to 1, this term u into u plus 1 divided by 2 factorial du, which is equal to 1 by 2 into 1 by 2 factorial means 1 by 2 into integral from 0 to 1, this is u square plus u du, that is u cube divided by 3 plus u square divided by 2 between the limits 0 and 1, that is equal to 1 by 3 plus 1 by 2. Here 1 by 2 into this, that is 1 by 2 into 1 by 3 plus 1 by 2, which is equal to 5 by 12. Now, the next term is integral from 0 to 1 u into u plus 1 into u plus 2 divided by 3 factorial tu, which is equal to 1 by 6 into u raised to 4 divided by 4. Here u into u means u cube. When we integrate, we will get u raised to 4 divided by 4 plus u square divided by u cube. Next is u cube plus u square between the limits 0 and 1, which is equal to 3 by 8. The next term will be integral from 0 to 1 by 24, that is 1 by 4 factorial means 1 by 24, that is u into u plus 1 into u plus 2 into u plus 3 divided by 4 factorial into this du, which is equal to 4 factorial means 24, 1 by 24 into, when we integrate, we will get u raised to 5 divided by 5 plus 6 into u raised to 4 divided by 4 plus 11 into u cube divided by 3 plus 6 into u square divided by 2 between the limits 0 and 1. Applying the limits 1 and 0, we will get value of this integral as 251 divided by 720. And so on. Using these values in this expression, we can write this as ym plus 1 minus ym is equal to h into Zm plus 1 by 2 into, here integral u du is 1 by 2. First integral is value of this first integral is 1. Therefore, we write Zm. The second integral is 1 by 2. Therefore, we can write 1 by 2 into del Zm, this plus 1 by 2 into del Zm plus value of the third integral is 5 by 12. Therefore, 5 by 12 into del square Zm plus value of the next integral is 3 by 8. Therefore, 3 by 8 into del cube Zm plus the value of next integral is 251 divided by 720 into del raised to 4 Zm plus etc., which is common. This is equal to h into Zm plus 1 by 2 into in the finite differences, we derived the relation between the backward difference operator and the shift operator E as E del is equal to 1 minus E inverse, where E inverse means the inverse shift operator. Therefore, we use this result del is equal to 1 minus E inverse here. Therefore, we can write 1 by 2 into 1 minus E inverse del Zm plus 5 by 12 into here also del. Therefore, we use 1 minus E inverse for del whole square Zm plus next term is 3 by 8 into del cube Zm, that is 1 minus E inverse whole cube Zm plus the next term is 251 divided by 720 into del raised to 4 Zm, del raised to 4 Zm plus etc. This is equal to, we can write this as y m plus 1 minus y m, which is equal to h into Zm plus 1 by 2 into here 1 minus E inverse of Zm, not del Zm. This is 1 minus E inverse of Zm, because del equal to 1 minus E inverse. Therefore, 1 minus E inverse Zm can be written as Zm minus 1 plus 5 by 12 into here we expanding 1 minus E inverse the whole square and apply the we do the corresponding operation. We will get this term as 5 by 12 into Zm minus 2 times Zm minus 1 plus Zm minus 2 plus the next term will be 3 by 8 into, first we expand 1 minus E inverse the whole cube and then use the corresponding operation. We will get this 1 minus E inverse whole cube Zm as Zm minus 3 into Zm minus 1 plus 3 into Zm minus 2, 3 into Zm minus 2 plus here minus Zm minus 3, not plus, minus Zm minus 3 plus the next term is 251 divided by 720 into del raised to 4 Zm plus etc. This is equal to, we can write this as h into 1 plus, we collect all the terms having Zm, we can write 1 plus 5 by 12, sorry here 1 by 2, then 5 by 12 Zm, therefore 5 by 12 plus 3 by 8, this into Zm minus 1 by 2 into, now we collect all the terms having Zm minus 1, therefore we can write here minus 1 by 2. In this term here minus 2 into 5 by 12, therefore we can write 5 by 6 plus in this term 9 by 8 z m minus 1 plus 5 by 12 into z m minus 2. Now, we collect all the terms having z m minus 2. Therefore, in this term 5 by 12 z m minus 2 plus in this 3 into 3 by 8 means 9 by 8 z m minus 2, this into z m minus 2 minus, now we collect all the terms having z m minus 3, here only one term 3 by 8 into z m minus 3, that is minus 3 by 8 z m minus 3 plus 251 divided by 720 del raised to 4 z m plus etc. This is equal to, we can write h into, on simplification this will become 55 divided by 24 Zm minus, this will become 59 divided by 24 Zm minus 1, Zm minus 1 plus this will become 37 divided by 24 into Zm minus 2 minus 3 by 8 into Zm minus 3 plus 251 divided by 720 del raised to 4 Zm plus etc., which is equal to h divided by 24 into 55 into Zm. We can write Zm as Ym dash. We used the notation Zm for Ym dash minus 59. Similarly, here we can write Zm minus 1 as Ym minus 1 dash plus 37, this is Ym minus 2 dash minus here 9, we taken 1 by 24 as common factor. Therefore, we can write here as 3 by 8 Zm minus 3 as minus 9 Ym minus 3 dash. This plus this into, next term is 251 divided by 720 del raised to 4 Zm into h. We write this term separately, 251 divided by 720 into h into del raised to 4 Zm plus etc. Now, in this expression, we neglect the fourth and higher order differences. Therefore, we can write Ym plus 1 minus Ym as h by 24 into 55 Ym dash minus 59 Ym minus 1 dash plus 37 Ym minus 2 dash minus 9 Ym minus 3 dash. That is, from this we can write Ym plus 1 as Ym plus these terms, that is Ym plus 1 is equal to Ym plus h by 24 into these terms. Here the error of approximation is (251) divided by 720 h into del raised to 4 y m dash. Del raised to 4 z m can be written as y m dash, which is equal to 251 divided by 720 into h into del can be written as 1 minus e inverse raised to 4 y m dash, which is equal to 251 divided by 720 into h into 1 minus e inverse all raised to 4, that is 1 minus e raised to minus h d all raised to 4 into y m dash, which is equal to 251 divided by 720 into h into this 1 minus e raised to minus h d can be written as h d, as h is very small. You can write this as h d raised to 4 y m dash, which is equal to 251 divided by 720 into, here h raised to 4 into h, that is h raised to 5, then d raised to 4 into d raised to 4 of y m dash, that is the fourth derivative, y m raised to 5. Fourth derivative of y m dash, that is the fifth derivative y m 5, which is equal to, we can write this as 251 divided by 720 into h raised to 5, here not h raised to 4, it is h raised to 5, because h raised to 4 into h means h raised to 5. Therefore, 251 divided by 720 into h raised to 5 into y raised to 5, y 5 means the fourth derivative of y at epsilon, where epsilon lying between x m minus 3 and x m plus 1. Therefore, we can write y m plus 1 as y m plus 1 is equal to y m plus h by 24 into 55 y m dash minus 59 y m minus 1 dash plus 37 y m minus 2 dash minus 9 y m minus 3 dash plus 251 divided by 720 into h raised to 5 y 5 epsilon. Y 5 means the fourth derivative of y of epsilon, where epsilon lying between x m plus x m minus 3 and x m plus 1. X m minus 3 less than or equal to epsilon less than or equal to x m plus 1. This formula is known as Adam-Bashforth's predictor formula. This is the predictor formula. Now, the Adam-Bashforth's corrector formula is taken as y m plus 1 is equal to this is the corrector formula, y m plus 1 is equal to y m plus h by 24 into 9 y m plus 1 dash plus 19 y m dash minus 5 y m minus 1 dash plus y m minus 2 dash minus 19 divided by 720 into h raised to 5 y 5 epsilon. Where y 5 means the fifth derivative of y. Here this epsilon lying between x m minus 2 xm minus 2 and xm plus 1. Xm minus 2 less than or equal to epsilon less than or equal to xm plus 1. This is taken as the Adam-Bashforth's corrector formula. This formula can be derived by assuming Z is equal to Zm plus U into del Zm plus 1, not Zm, it is Zm plus 1, U into del Zm plus 1 plus U into U plus 1 divided by 2 factorial into del square Zm plus 1 plus etc. That is, this is the Newton's backward difference formula for Z at the point Zm plus 1, and proceeding as before, we can obtain this corrector formula. To apply Adam-Bashforth's predictor corrector method, we require 4 starting values of y. Hence, these methods are known as multi-step methods. In the previous class, we discussed the Milne's predictor corrector method, which also a multi-step method, whereas the previously discussed methods, Taylor series and Runge-Kutta methods, are single step methods. Now, let me conclude this session. Thank you for watching the class. Have a nice day.